Okay, we're going to start Unit 4. So our first set of notes in Unit 4 is going to be about exponential functions. So I want you to please read this description. We're starting with 1 penny on the 1st of January, and then we're seeing how much money we would have on the 31st. Make sure that you're doubling every day. So please pause this and fill out the rest of the table. Okay. If you paused and filled out the table, your table should have looked something like this, where on the last day of the month, you would have made $10,737,418.24. Maybe a little bit more than you would have predicted, but that's what exponential functions do. So exponential functions are functions where we have variables in the exponent. So I'm going to grab my calculator and we're going to graph x squared and 2 to the x, and we're going to compare the graphs. Delete everything that's there. So x squared and 2 to the x. And honestly, the original graphs don't differ as much as we might expect because we're on a pretty small window. So I actually want to go and look at the table. Nope. There we go. And I want to compare the y values. So here, my y values are pretty similar, except for as we go further up, you should notice that on x squared, which is my y1, the numbers are increasing, but not nearly as quickly as the values for 2 to the x. Here, by the time we get to 15, we have 225, that's 15 squared, but 2 to the 15th power is 32,768. So the thing about exponentials is that exponentials, so 2 to the t grows very quickly. Okay. Now, on this next page, I am just going to show you because these tables I got just by putting my calculator back on auto, or back on ask from auto. So I went over here, I put 2 to the x. I'm only going to show you one of these because they get pretty redundant. 2 to the x. And then I went back to window, and then I changed this to ask. And then I went to my table, and I put in these values. So negative 92.7, negative 10, negative 2.5, negative 1.9, 0, 1.4, 2.6, 10, 89.54. And that's how I got my table. Now, I do want to make a note to you that that e that you see sometimes means exponential notation. So 1e to the negative 28 means that I would move the decimal place over to the left 28 times. So it would be decimal point, 27 zeros, and then a 1. So imagine what an infinitely small number that is. 9.8 e to the negative 4 written out would be 0.00098. And then if we were looking at 9e to the 26th, a positive number means move the decimal point to the right. So 9e to the 26th is the same as a 9 followed by 26 zeros. So think of how gigantic a number that is. So that is what I did for all of these tables. I'm not gonna do that over and over again. You certainly can, or you can just copy down the answers that I have here. But for every exponential function, we have a domain of all real numbers, a range of 0 to infinity. So exponentials will only ever give you positives because if we have a positive base to any power, my answer is always going to be positive. They all have an intercept at 0, 1 because any number to the 0 power is 1. And then we have an asymptote at y equals 0. Let's look at the graph. So that asymptote is only on the left side. On the right side, y goes up toward infinity. But here we're going to get closer and closer to 0, but we're never actually going to touch. Okay? So I graphed y equals 1.01 to the x and y equals 10 to the x, and they both have this same general shape. There we go. Only I would say that how quick they grow depends on the base here. So the bigger the base, the faster this curve goes up. So for example, if I put y equals 10 to the x on the same graph as y equals 2 to the x, you'll see that the red line starts increasing way faster than y equals 2 to the x. So the bigger this base, the faster this line goes up. Now, for exponential functions with a base between 0 and 1, again, I filled these tables in with my calculator, so you can either do that yourself or copy them down. But domain, range, intercept, and asymptote are the same. If your base is between 0 and 1, none of that changes. The only thing that changes is that your graph flips around the y-axis, and that is because negative exponents make fractions, and a negative exponent, negative in the x means to flip around the y-axis. That's one of our transformation rules. So if your base is between 0 and 1, your graph looks the same. It's the same general shape, just reflected over the y-axis. Okay, and every graph that has a base between 0 and 1 will have this same general shape. Okay, so let's write down some of the generals here. There we go. So in general, the shape of y equals a to the x when a is greater than 1 is this, where the steepness of my curve is determined by the a value. The bigger a is, the steeper the curve. They all have a domain of all real numbers, a range of 0 to infinity. Notice that parenthesis on 0, 0 is not included. An intercept at 0, 1, and again, that's because it doesn't matter what a is. Any base to the 0 power is 1. And an asymptote at y equals 0. And then if my base is a fraction, my general shape, this is pen die, my general shape is the same as this, only reflected over the y-axis, so flip it over. And then domain, range, intercept, and asymptote are the same. So are these the graphs of functions? Yes. They would pass the vertical line test. And then a few quick notes that we do not do y equals a to the x when a equals 1 because 1 to the x is always 1. So since 1 to the x is always 1, y equals 1 to the x is actually technically a constant function, not an exponential function. And then we do not do them when a is less than 0 because they are not continuous. The graphs of these are so messed up that your calculator can't even graph them. So like if you tried to put y equals negative 2 to the x like that in your calculator, it can't even like get you a normal graph. Give it a shot, you'll see. But these graphs are not continuous, they're not good functions, so we don't work with them. So if I was going to graph y equals 5/7 to the x, if we were just doing a general curve, that would be the one that is decreasing, still going through my 0, 1 intercept. Domain range, intercept, asymptote, same as before. And then 7/5 x, domain, range, intercept, asymptote, also the same. It's not the world's best graph, but I think you get the point. So these two graphs are the graph of one another reflected over the y-axis because they are reciprocals, meaning that since 5/7 to the -1 is 7/5, that -1, when we put it up with the x, would need to reflect over the y-axis. Okay, so again, I would like for you right now to pause this and fill in your tables, and then try to take some guesses on what you think domain, range, intercept, and asymptote are for these, because they change a little bit, but not a whole lot. Okay. Another moment where the only thing that I could do is hope that you actually paused the video and did it, but let's take a look at the answers here. So here were my tables. Notice that domain and range are the same for all of these. Asymptote is the same for all of these. The only thing that changes if we have a constant in front is the, well, hang on, range is not the same for all of them. That one had a weird range. The main thing that changes is the intercept. So if 3 to the 0 is 1, then 1 times 2 is 2. So whatever this number in front is, if there's a constant in front, then that is your intercept. And if that constant is negative, then that negative reflects your graph over the x-axis, which means that your range reflects over the x-axis and becomes the negatives. Okay? So again, let's write that down. Oh, hello, loud noise from my computer. Domain is still all real numbers. If we have a constant in front, domain is still all real numbers. Range, if c is greater than 0, if c is positive, the range is positives. If c is negative, the range is the negatives. And then the y-intercept is always going to be 0c, whatever that constant is. Okay, so here, remember that the basic equation for these exponential functions is y equals c to the a, where c is my y-intercept. So here, I'm always going to start with y equals c times a to the x. What did I say before? That's what I meant. Y equals c times a to the x. Here, I have a y-intercept of 0, -3. So that means that c is -3. So then y equals -3 times a to the x. And now they've given me the point 1, -2, so that means when x is 1, y is -2. So I'm going to plug those two values in and then solve for a. -2 equals -3 times, a to the 1. So that means -2 equals -3 times a, because a to the 1 is just a. So a is -2 divided by -3, which is 2/3. So then my equation for this is y equals -3 times 2/3 to the x. And so here we have a c value of 1/4. And then this is my x and this is my y. So I'm going to plug in all three of those and solve for a. So 1/9 equals 1/4 a to the -2. I'm going to multiply both sides by 4 to get rid of this 1/4. 4/9 equals a to the -2. Now, I'm going to take both sides to the -1. And then 4/9 to the -1 is 9/4. Remember, the rule for exponents is that when we take a power to a power, we multiply the powers. So -2 times -1 is a positive 2. So that means 9/4 equals a squared. And then I'm going to square root both sides. So the square root of 9 is 3. The square root of 4 is 2. So that means a equals 3/2. So then my equation is y equals 1/4 times 3/2 to the x. Okay. So the other thing that I want to tell you about is E. E is an irrational constant that we use in math, just like pi. This is an approximation of E to some gigantic number of decimal places. For us, 2.718 is fine, but really you don't even need to know that because your calculator has an E button. It is right here above ln. We're going to talk about ln soon. But E is always used as the base of an exponential function. So if in the calculator you press the E button, you're going to see that the first thing that the calculator is going to do is prompt you, can you see that? Prompt you for an exponent. So E is always the base of an exponential. It's never used by itself. E has a lot of real-world applications. Banks use it, chemists use it. We're going to look at a few real-world applications of E as we go through this unit, but know that E is one of those things that will come up over and over and over again in other math classes as well as in a bunch of your science classes. Okay, so the last thing that we're going to do as part of these notes is solve some exponential equations. So if you can, the goal here is always going to be to get bases the same on the left and the right, because if the base is the same, then the exponent has to be the same. That's the only way for the equation to be equal. So we're always going to ask ourselves, what can I do to force same bases? So is there a way to rewrite 4 so that it is in base 2, or is there a way to rewrite 2 so that it is in base 4? So here the easiest thing to say is probably that 4 is the same as 2 to the second. Now these have the same base. And since 2 to the second equals 2 to the x, the only way for that to be true, since the bases are the same, is if the exponents are the same. So then this would be 2 equals x, or x equals 2. So again, once you have same bases, then you're just going to set the exponents equal to each other and solve. Okay, so is there any way to rewrite 1/8 as 2 or 2 as 1/8? Well, I know that 8 is 2 to the third, which means that 1/8 is 2 to the -3. So keep in mind that a negative exponent means to take the reciprocal, like I said a couple minutes ago. So 1/8 is the same as 2 to the -3. And again, just like before, if 2 to the -3 equals 2 to the x, since they have the same base, the exponents have to be equal. Now, a lot of times we're going to have to change both sides so that they have the same base. So here I can rewrite both 625 and 1/5 so that they are in base 5. 625 is 5 to the 4th, and 1/5 is 5 to the -1. Our rule for exponents is if we have a power to a power, we multiply. So 5 to the 4th equals 5 to the -x, -1 times x. And now that the bases are the same, I can set the exponents equal to each other. So then this would mean 4 equals -x. Divide both sides by a -1, and x equals -4. Okay, so then here, the bases are all the same, but in order to be able to drop the base and set the exponents equal to each other, you have to have one thing equals one thing. So here we have 2 e's on this side, which is no bueno. I got to combine those 2 e's into 1 e in order to be able to drop the bases. So here, remember the exponent rule is that when you're multiplying, you keep the base, and add the exponents. So e to the x plus 2 equals e to the negative 3x. And now that the bases are the same, and now that I only have one e on each side, I can get rid of it and just say x plus 2 equals negative 3x, and then subtract this x from both sides, and divide both sides by negative 4, and then reduce. Okay, last but not least for this section, 9, 27, and 3 can all be written as base 3. So 9 is the same as 3 to the second to the 2x. 27 is the same as 3 to the third to the x squared, and then we'll keep this as 3 to the negative 1. So again, the rule is when you take a power to a power, you multiply. So this is 3 to the 4x. This is 3 to the 3x squared, and that's still 3 to the negative 1. And then the rule is that when you have the same base, you keep it and you add the exponents if you're multiplying in between. So this becomes 3 to the 3x squared plus 4x equals 3 to the negative 1. Now, a long time ago, I told you that you needed to know how to factor quadratics because I was going to make it a part of every single unit. So there it is. There's your quadratic equation. When I get rid of the bases, I have 3x squared plus 4x equals negative 1. So 3x squared plus 4x plus 1 equals 0. That's going to be 3x squared plus 3x plus 1x plus 1. When I factor 3x, x plus 1 plus 1x plus 1, 3x plus 1, x plus 1. So 3x plus 1 equals 0, x plus 1 equals 0, x equals negative 1/3, and x equals negative 1. Okay, it's a promise that I made to you that I intend to keep. Okay, so here we have a colony of bacteria growing at a rate of P of t equals 150 e to the 0.2 t, where t is time and P of t is the number of bacteria measured in grams. So I guess they're weighing the dish. But the initial amount of bacteria would be when time equals 0. So if we do P of 0, we'll get 150 e to the 0.2 times 0. But 0.2 times 0 is 0. And e to the 0 is 1. Anything to the 0 is 1. And then 1 times 150 is 150 grams. So you should know that any time you're asked for initial amount, it's always going to be the number in front of your exponential. And so then after 5 minutes, it would be 150 e to the 0.2 times 5, which let's just do over here. So 150 e to the 0.2 times 5. So that's 407.7 grams. And then P of 10 is 150 e to the 0.2 times 10. So 11,008.4 grams. Now notice that our time doubled, but the weight of our bacteria almost tripled. So this is not linear. You can't expect that when time doubles, the number of things will double. An exponential function will definitely grow faster than that. So now is another time when I'd like for you to pause the video, try the last one, and then when you're done, unpause. So like I mentioned before, initial amount is always going to be the number in front. So the initial amount here would be 98 grams. And then after 1 day, you would have, 98 e to the negative 0.067 times 1. You would have 91.6 grams. After 8 days, you would have 98 e to the negative 0.067 times 8. You would have 57 grams. Okay, so that is our introduction to exponential functions. We're going to circle back and talk about them again a little bit later in the unit. But for now, you are ready to do your first homework in Unit 4.